Okay, so here we've got the notes for section 5 of unit 3, the Poisson distribution. So Poisson distribution recurs to events that occur over a specified interval, so usually a period of time, distance, things like that, some similar unit. So it helps you figure out how likely it is for an event to occur in that unit. So, the example down here is like hurricanes per year, or, how many dandelions do you find per square mile, things like that. So here's the formula for it. So this formula should hopefully be printed in your notes. So it's P of x, the probability of x events occurring, is mu to the x. So mu is the mean. E is Euler's number here. It's a value. There's a button on your calculator for it. Raised to the negative mu power all over x factorial. Just remember, factorial is the number counted down. So here are the requirements for the Poisson. The random variable x is the number of occurrences of an event over some interval, so it can't just be forever. The occurrences have to be random, they must be independent, and they must be uniformly distributed over the interval being used. And then down here for the parameters, for sort of Poisson, the mean is mu and the standard deviation is the square root of mu. All right, so example 1, for a recent period of 100 years, there were 530 Atlantic hurricanes. Assume that a Poisson distribution is a suitable model. Find mu, the mean number of hurricanes per year. So normally when you see mean, you have a list of numbers that you have to add up and divide by however many there are. But since I don't have the list, I know there are 530 total over the 100 years. So the average, the mean, is 530 divided by 100. So there were on average 5.3 hurricanes per year. So if Px, the probability of x hurricanes in a randomly selected year, find P0, P2, P9. So the likelihood there are no hurricanes, there are 2, there are 9, so on and so forth. So that's using this formula up here. So for P0, the likelihood there are no hurricanes, that's going to be the average. So 5.3 raised to the 0th power, because that's my x value, times e to the negative 5.3 all over 0 factorial. And all that fun stuff just goes in my calculator. So 5.3 raised to the 0th, now that's 1 because anything raised to the 0th, times e to the negative 5.3, all divided by 0 factorial, which actually is a special case. 0 factorial is actually just 1. So this comes out to be 0.00499. So a 0.5% chance, if you make it a percent. So for P2, that's going to be 5.3 squared times e to the negative 5.3 all over 2 factorial. And P9 is 5.3 to the 9th times e to the negative 5.3 over 9 factorial. So you notice this part here, the e part, that doesn't change because that's just based off the average. It's only this exponent, that number, that should change. So 5.3 squared times e to the negative 5.3 divided by 2 factorial. So this is 0.070, so a 7% chance, and 5.3 to the 9th times e to the negative 5.3 divided by 9 factorial is 0.0454. So if you actually want to tack the 1 on there to get the 3 significant digits. Okay, so there are actually 2 years with no hurricanes, 5 years with 2 Atlantic hurricanes, and 4 years with 9. How would these actual results compare? So if this is the probability, I can take this number times 100, and that should give me the number of years that have no hurricanes, have 2 hurricanes, have 9 hurricanes. So if I take 0.00499 times 100, there should be about a half year, which doesn't really make sense, with no hurricanes, or 1 year if you round it up even more. So for 2 hurricanes, there should be about 7 years, which not too terribly far from 4. And for 0.0454 times 100, so this is for 9 hurricanes, there would be about 5 years, which is pretty close to 4. So it's not perfect, but they are relatively close. 0.5, you know, it's not terrible. All right, so on the back side here, the Poisson distribution as an approximation for the binomial. So you can use that formula to approximate the binomial instead of doing the n factorial over n minus r times p to the nth, so on and so forth, from the previous sections, if these two criteria are met. So you have to have more than 100 measurements, and n times p has to be less than 10. So example 2 says down here, the main pick 4 game, you pay 50 cents to select a sequence of 4 digits, such as 2, 4, 4, 9. If you play this game once every day, find the probability of winning at least once in a year with 365 days. So n, we're going to play 365 times. P is the probability of winning. So if there's 4 digits, there's actually 10,000 possible values, and only one of them wins. So n is more than 100. If I take n times p, so essentially is the average less than or equal to 10, so that's going to be 365 times 1 over 10,000, or 165 divided by 10,000. That is 0.0365, so that's definitely less than 10. So if I use the Poisson distribution, now I'm going to do this problem backwards. Only at least once in 365 days. So I could win 0, 1, 2, 3, 4, 5, 6, 7, all the way to 365. The long way to do this problem would be between the likelihood of winning once, and then the likelihood of winning twice, and then thrice, and then 4, and then 5, and then 6, all the way up to 365, and then you have to add them all up. Or I could find the likelihood of never winning 0 times, and subtract that from 1. Because if you think about it, the possibilities are I could win never, once, twice, thrice, 4 times, blah, 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 all the way up to 365. So the question wants that probability. But the two probabilities have to add up to 1. So whatever this is, if this is the probability I'm looking for, this value here has to be 1 minus x. Or vice versa, if I find this one's 1 minus x, because these two things have to add up to 1. So if I can find this guy, I can subtract it to 1 to get that, because that's all the rest of the options. So I'm going to find p 0. So that's the average, so 0.0365 raised to the 0th times e to the negative 0.0365 to the negative average all over 0 factorial. So that's going to be e to the negative 0.0365 divided by 0 factorial. This comes out to be 0.964. So there's a 96% chance that I never win. So the likelihood that I win at least once is 1 minus the likelihood that I never win. So this is 1 minus 0.964. So 0.036 is the likelihood that I win at least once. So very, very small. It's very, very hard to win the lottery. Which brings us to the end of our notes.